Hello everybody, I hope you're having a good weekend. As promised, I am going to make a video showing how to graph the data for the t-butyl chloride kinetics. So let's get to it. One of the things I want to start with is you have to be very aware of your fundamental principles of general chemistry. We are being asked to calculate the moles of RCl, which in this case is the t-butyl chloride. So when you see t-butyl chloride, RCl, it's the same thing for this spreadsheet. So the moles of RCl at time zero, they're asking you how many moles of t-butyl chloride were present when I added it into the Erlenmeyer flask. I added 1 milliliter, but we are learning now from equilibrium that sometimes not all reactions actually go fully forward to completion. We will explore that later in lab 6 for methyl acetate. But for now, we have to assume that not all of the t-butyl chloride actually became HCl. It's possible some just stayed as t-butyl chloride. So you cannot use the density of t-butyl chloride to calculate the grams of t-butyl chloride and calculate the moles of t-butyl chloride. Do not do that. That is not going to give you an accurate answer. Instead, we are going to be calculating the moles of t-butyl chloride that we started with using stoichiometry. So if you're a little rusty on stoichiometry, as I mentioned at the beginning of the semester, you need to catch up. So I will be doing a quick annotation here if you can follow along. Basically, we have t-butyl chloride, and then that reacts with water, and that is going to give me HCl, and it's going to give me t-butyl alcohol. But that's not important. I'll still write it. T-butyl alcohol. Okay? Everything is 1 to 1. There is only 1 mole per 1 mole per 1 mole per 1 mole. 1 mole of this will react with 1 mole of this to make 1 mole of HCl and 1 mole of t-butyl alcohol. So if you know the concentration of one, you know the concentration of the other. If you know the moles of one, you know the moles of other. That is the whole purpose of stoichiometry. That is why we spent so much time last semester trying to learn what these things mean. This is simply how many of something do I have for every something else. In this case, everything is 1 to 1 to 1 to 1, which is perfect because we can measure one thing and we can make assumptions about the other. So in the reaction, at the very end, let's assume this reaction does go to completion, right? At the very end, all we will have is HCl. And if we titrate HCl with NaOH, and we know how many moles of NaOH because that's what our molarity tells us. Remember, molarity is moles divided by liters. So if we multiply by a known volume of a known molarity, we can calculate the number of moles right there. And if we know the numbers of moles of NaOH, and we know that it's 1 to 1, then we know the moles of HCl. But wait, there's more. If we know the moles of HCl, because it's 1 to 1, we know the moles of t-butyl chloride. I hope that makes sense. This is why we needed to take into account the total volume that we used of NaOH, because the total volume is then assumed to be 1 to 1 with HCl, which is 1 to 1 with t-butyl chloride. And therefore, we can calculate how many moles of t-butyl chloride we started at time zero. So you can see in this example down here, they added 7.5 more milliliters on top of their 20 milliliters that they had added. So 20 plus 7.5 gives you 27.55 milliliters. Remember, molarity. So we can calculate the moles of the t-butyl chloride by calculating stoichiometrically backwards. So we have 0.02755 liters of NaOH. The concentration, I believe, was 0.255. I think it was different for both days. You guys should have written that down. Moles per liters. Again, the liters cancel out. So if I do this calculation, I will fill in right here in column 6 what moles I have of t-butyl chloride. So let me go ahead and clear these annotations, clear all the drawings, get rid of that. And now I can go ahead and actually type stuff in here. Okay, so here's how I'm going to do this on Excel. We're using the formula sheet. Equals, we need the volume total of NaOH that we used. So that was 27 milliliters. Remember, the molarity that we're going to be multiplying to cancel out is moles per liter. So we have to convert milliliters to liters. How do we do that? We divide that by 1,000. That gives me my 27 moles divided by 27 milliliters divided by 1000 gives me 0.27 liters. That is not done. Make sure that you finish your formula before you submit it. So that is my liters. Now I need to calculate my moles. How do I do that? I have to multiply by my molarity. Volume times molarity gives you moles. So there's my molarity right here, 0.255, and that is going to be that number right there. So again, checking the formula, cell E18, which has my total volume. So volume divided by 1000, that gives me liters. Liters times molarity in cell A18 right over here gives me the total number of moles. And since this is at time 0, this is true for all of this column. This entire column is going to have the same number every single time. So you can just drag that down and see the number. If you see this happen here where the number doesn't work, what's happening is that Excel is automatically doing the math for the next cell and the next cell. You need to keep cell A18. In other words, in my case, the cell where I put my concentration. For you, it could be any other number. But in this case, you need to keep this cell constant. The way you refer to a cell constantly, in other words, it's called an absolute reference, is you type in money before the letter and money after the letter. When I do that, I fix the value to that cell specifically. So when I scroll down, oh, it still doesn't work. What's going on? Now E19, what is E19? That is my volume. See, my volume is also changing every time I use this down. So what I'm going to do is, once again, I'm going to make that number or that cell, and for you, it could be anything else. Money, E, money, 19. And that should give me that. 18, not 19. Oh my goodness, so many mistakes. This is why I'm doing this with you guys, so you can see what happens. There you go. See? So now that I fixed the absolute reference, when I go ahead and take this down, all the numbers fill in with that absolute reference. If you don't like that, you could just manually type it all in once you get the first calculation. It's probably a lot easier. I'm just showing you that if you want to keep one value of the cell the same, you can use the money sign. All right, let's not get too focused on that. You can always type in the values manually on your own. But that is how we calculate the moles of the t-butyl chloride at time 0. We're doing it from the moles of NaOH, from the volume of NaOH, not from the density. So please don't make that mistake, regardless of what I may have told you in the past. All right. So now we can move on to this next one right here. Moles of t-butyl chloride reacted at time t. So this is where we say, okay, how many moles of t-butyl chloride have reacted at a specific time? Well, at a specific time, we have been adding volume of NaOH. And the NaOH, just like I showed you in the annotations earlier, reacts with the HCl. And so every time we add, we have a reaction. So the moles of RCl are equal to the moles of NaOH added because of the formula. Okay? So to calculate the moles of NaOH, remember, volume times molarity. Well, here the volume is 0 in column 4. The volume is 0. So the moles of RCl that react at 0 are 0. Remember, at the beginning of any chemical reaction, there is no product and there is only reactant. So at time 0, there's no reaction. It's just 0. However, you can see here on column 5, we added 2.05 milliliters of NaOH. So those 2.05 milliliters, in other words, we're going to be using column 4, the total volume of NaOH added at time t, to calculate the moles of RCl at time t. So here, we're going to take this value, which is 2.05. That's going to be in cell D4. So I'm going to set this to equal. I'm going to click the volume right here from column 4. I don't know why it's doing that specifically. There it is. The downside of using columns, eh? I'm gonna manually type the cell here. D4. There you go. Perfect. So cell D4 divided by 1000, because we're converting to liters, and we're going to multiply that by the molarity of NaOH. Again, molarity times volume gives you moles. Okay? So there is my volume right there. And then I'm going to multiply that by my molarity. Remember, the molarity needs to be an absolute reference. So I'm going to do times, and the molarity is right here, 0.255. I want that cell to stay A18. So I'm going to put money and money around the letter, and that gives me my moles reacted from the volume. So this number comes from column 4 divided by 1000 times my molarity. You can put your molarity everywhere. You can make it a part of your formula. As long as you're getting the right calculations, the right numbers, it should be good. Then you can just drag this and fill it down And the number should be increasing. This is also where you got to use some common sense, right? If you see this number not going up as time goes on, because as time goes on, more stuff reacts, then clearly there's something wrong with the calculations. So don't just type in numbers, don't just be doing stuff. Make sure you're actually observing the trends in the numbers. You go from 5 times 10 to the minus 4 to 1 times 10 to the minus 3, 1.5 times 10 to the minus 3, and you see now it goes to 2 times 10 to the minus 3. So since it's going up, and I checked the formula, I'm assuming that this is going to be correct. We'll find out when we graph it, right? That's ultimately when we know. Okay, moles of t-butyl chloride remaining. In other words, initial moles that we started with minus moles reacted equals moles remaining, right? Initial minus a difference equals final. So here we have our initial moles in column 6 right here. We have to subtract them from the number from column 7. So it's going to be column 6 minus column 7. So that's going to equal to this one here, column 6. I guess let me try if this works. I've never tried this before. Minus column 7. And then enter. Okay, wow, that actually worked. It actually works like that. That's cool. Okay, let me fill it in. And again, this is the moles remaining. This is the concentration of reactant. As the chemical reaction moves forward, the concentration of reactant goes down, the concentration of product goes up. So this number should be going down, and sure enough, you see that it's going down. So it's looking pretty good so far. Alrighty? And then column 9, now they're asking for the concentration. Again, if you see brackets with the chemical formula inside, that's 90% asking for molarity, concentration in molarity unless otherwise stated. So this here they're asking for the concentration of the t-butyl chloride at time t, RCl bracket sub t. Or you can just say RCl at time t. Well, the concentration is moles divided by liter. Column 8 gives me moles. So column 8 is moles, again, equals column 8. And then divided by, actually, I'm not going to do this in terms of columns. I'm going to do this by cell because I need to be able to change the whole thing, divide by 1000. Okay, so not column 8. If you're using columns, you'll have this problem, but you can just type in, this is H3. So H3 minus, no, sorry, not minus. I am doing division. Moles divided by liters. So column 8 divided by column 5, total volume of solution. So divide that by column 5. And column 5 needs to be divided by 1000 to give me the stuff in liters. Hold on. I don't like that it's doing the column thing. E3. Okay. E3. Enter. There it is. It gives me that. And then E3 needs to be divided by 1000. Otherwise, the number is too small. There you go. Thank you for your patience. I really appreciate it. And again, I like to show when I struggle too, because when I fix it, you could also see what sort of steps you can take to troubleshoot to fix it yourself. Excel is a skill. If you master it, you're going to have a job forever. Anyway, so here we go. We have the concentration in moles, sorry, in molar, big M. That's already implied by the brackets. You don't need to be specific with that. So 0.069 molar. And then we can take this and actually drag it down. We don't need to do the money sign here. We don't need to absolutely reference. And again, the concentration should be going down because the reactant is reacting. So 1, 2, 3, 4, 5. Okay. It goes from 0.06, 0.05, 0.04. It's going down. It makes sense. Column 10, very easy. That's just the natural log of column 9. So you just put ln. And again, I'm having an issue inputting columns. So I'm just going to manually put I3 right here. And that selects that value. And there you go. And yes, it's okay if it's a negative number. You should know that natural logs of fractions or decimals are negative. So there you go. Okay, so that is how you calculate the remaining data for the remaining columns. The next step is we have to make the graph. You have to make 2 graphs. The first graph has to be concentration of t-butyl chloride at time t versus time. Remember, this is a rate experiment. A rate of reaction is in molar per second. Molar per second. Molar per second. Why do I say it 3 times? Because what is the formula for slope? Here, I'm gonna get my annotations again. What is the formula for slope? Slope is equal to y over x, or specifically delta y, delta x, right? Change in y, rise over run. We learned it so many different ways. So if you're gonna have something and linearize it, or you're gonna try to graph something to see if maybe you get a line out of it, you need to put what you want on the y and what you want on the x so that when you do your slope, you get the units you want. So in this case, since I want molar per second, that means my y-axis is going to be molarity and my second axis is going to be my x-axis. That's how you decide what to put on a graph. So this way, when I do a slope calculation, y over x, I get molar per second. The slope, assuming it's a line, will tell me the speed or the rate of the reaction. Pretty cool, actually. So hopefully that makes a bit of sense. I'll go ahead and clear my annotations. And then let's go ahead and actually get the graph going. So to do that, I'm going to move the thing over here so I can actually see the menu. Let me get rid of the annotations. There you go. I'm back to Excel. We're going to insert a graph, just like we always do. Insert. Here's the chart. Scatter. Again, you should get something clear and clean. If not, it's okay. You can always go to select data. So click on the chart, chart design, select data. Again, let's move this out of the way. We want it to not take up too much space. And again, what goes on the y-axis? Molarity. Molarity per second is what we want. So M has to be your y. So that's column 9. So let's select our data, add, and this is simply just going to be whatever you want to call it. You don't even have to name the series right now. Just select your data. Your x value, what's on the x-axis? Time. So your x-axis is going to be total elapsed time. Boom. Y value, again, get rid of the bracket 1 bracket. I still don't know why that's there. If you guys figure it out, we'll talk about extra credit. Your y-axis should be your concentration at time t. So here it is, concentration at time t. Look at that. That is a beautiful curve. Alrighty. And then I'm just going to click OK. And then just click OK. This is my first chart. Be specific with your title, guys. Usually the title is going to be what it is we're looking at. In this case, it is molarity or concentration. So let me just do that actually. Let me do concentration of RCl at time t versus time t. And then in seconds. Make sure you put your units, please. So then your y-axis should be concentration. You can go ahead and select the chart elements that you want to add. Title, axis title, you want your axis title. In this case, I don't think you need a legend, and I think the instructions in the lab say that there is no trend line. But for the sake of full understanding, please go ahead and click a trend line in there, and then you should get all those things right there. Your values, again, y-axis, it is your concentration of t-butyl chloride at time t. And then your x-axis is simply just going to be time in seconds. Make sure you specify your units, please. I can't tell you. Units, 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 units. If I continue to see an issue, I will start grading for units. So please just remember your units, guys. It's very easy. You need to be very specific. So here we go. We have a nice looking graph. This reaction is first order. So we are not going to get a line just plotting the concentration of t-butyl chloride at time t versus time. It actually is supposed to be looking kind of like this. And if you look at the first order equation, you're going to see that it's actually an exponential. So here is your exponential. You can click exponential in the trendline options, display the equation on the chart, and you can see that right there. And you can display the r squared value as well if you go back to the trend line. There you go, r squared value. All right. And actually, if you look at the not integrated first rate law, you can see that this right here already has one value for k, but it's based on an exponential graph. I don't know how to make this bigger, but you can see it right there. You can go to File, Home, oops, Home, and then there you go. That's a good way to make the number bigger. So there you go. So see, so this number here should be your initial concentration, e to the negative kt. So this is your negative k. The only problem is Excel rounds it up to literally one significant figure. So if you do calculations with this k value, because it's such a small number, you're not going to get the right answers. Also, it's not exactly a perfect fit. You could see here that it's a little bit, the trend line is a little bit below, and then it kind of goes a little bit above. It's an average of all the data points. In other words, the data is not really that useful. I just wanted to do this to emphasize it. You don't have to include this one, but it does demonstrate understanding of the subject. So if you do this, I mean, unless the chemist is having a really bad day, I don't think he's going to take points off for this. If he does, talk to me. I'll give you your points back. But here's your first chart. You do need to turn this in. Please make sure that you are labeling your axis with your units and make sure that your scale is good. Like there's no reason that this should be going all the way to 10,000. You can cut it off at 2,500. There's no reason this could even needs to go to 0, but since it fits on the graph, this is perfectly fine. So there we go. We got one of our graphs. We're okay. Let's do the second one. I'm going to move this down here so you guys can see the next one. The second graph that we're going to make is going to be a natural log of the concentration at time t versus time. So we go back up here, scatter. We inserted, I think it automatically selected it. Yeah, there we go. I need to insert a new one. So insert, scatter, there we go. I'm going to move it over here. And then again, I have to select my data. It's only one data set. I don't need to be doing series this time, so I can ignore the name. X values, again, what's on the x-axis? Total elapsed time. I can't see because of the microphone. There we go. And then what's on the y-axis? The y-axis is going to be your natural log of the concentration. There you go. And then this should be a line, actually. This should definitely be a line. So I'm going to click OK and get rid of this right there, series 1. Okay, there you go. So here's my chart now. You can see the scale's a little bit off. So I'm going to go and put format axis. You can choose what range you want it. So here, maximum is 0. Well, it seems like my maximum is negative 2.5. So actually, I'm going to put negative 2.5 as my max. And then I am going to, let me see, is the x-axis okay? Yes, the x-axis looks okay. So let me just click that. And you can see it changed. And you could see here too that the x-axis is on top. You could also just put that on bottom. So let me go ahead and also do that. Let's see, format axis. And then I think you can select where it says crosses at. Here it is, vertical axis crosses at the minimum axis value. Nope, automatic. I think you have to click on the y-axis for that one. Let me see. Format axis, minimum, maximum, axis value, axis value. Oh, it says maximum here. I don't know why it does that. That's interesting. Values in reverse order? No. Actually, that kind of works. Okay. Well, I mean, it's negative, it's going up, but we know that negative numbers are actually going down. It should still give us good data. So there you go. I fixed the chart. Again, the goal of this is not to be like, oh, this guy doesn't know how to use Excel. A lot of people don't know how to use Excel. We learn as we go as we need to do so. Only people who deal with Excel on a regular basis all the time actually learn Excel. So if you want to learn how to do it, cool. Otherwise, play around with it. You'll figure some stuff out. You'll learn. Anyway, the chart here is called the natural log, so ln of what? Of the concentration of RCl at time t. You can just put at t to make it easier versus time in seconds. There you go. And then if you do a trend line, well, here we go. This one actually is more linear, so add trend line. You can see linear right there. Then you can put display equation on chart and then display the R-squared values. Make sure you always do that. And then here, this should give you the y-intercept is going to be the natural log of the original concentration. And then this number here, 0.007, that should be your slope. And what is the slope again? What is the slope? The slope is y over x. So that slope right there is your rate. It's your molarity per second. Okay? Or I think it's K. I don't really know. Make sure you take a look at it. Oh, actually, no. Y is rate. I don't know anymore. You guys double check. I'm just teaching you how to make the graphs. Anyway, so you have your data here. This is how you get your graph. This is how you get your data. Now you have two beautiful looking graphs. And then make sure once again that you add your chart elements, axis title, legend. No, you don't need a legend here. Make sure you keep your trend line. And then make sure for the love of, you know, supernatural beings, please make sure that you are putting labels on your trend lines. So this is the RCL at time t. And then here is just time in seconds. And there it is. You have your two graphs. Make sure, try to see if you can print each graph on an individual page. And also, if you guys can do a little description at the bottom, for example, tell me what this graph is. This is concentration figure 1, right? Figure 2. And write a short description about the figures. You don't have to do that yet, but you will have to eventually. So just get some practice right now while you get the chance. Also, make sure you read your lab book because you're also required to add to the spreadsheet. It says here, I believe, that you also have to add temperature. You also have to add the volume finished. You have to add the concentration. Oh, and the half-life. I almost forgot about the half-life calculations. So this one's actually pretty straightforward, right? You look at your y-axis. In this case, you see your initial concentration. You can hover over the point and it tells you what it is. So there's your concentration right there, 0.06955. That is your A. That is your A. Okay? And then if you go down, well, let's see. This whole thing took, what's the total time right here? Does it show? Let me see. Can I scroll over the data? Can I hover over the data? It's not showing me. So let's go here and take a look. This is why we have this. So the concentration of RCl at time t, well, what's half of 6.9? That's almost 7, so 3.5. So roughly around here at 897 seconds, you got half of the original concentration. So from looking at the graph, at 897 seconds, right here, at 897 seconds in this example, the concentration of t-butyl chloride was roughly half of the original concentration. So that is your half-life from estimation from the graph. You look at where you started and you look at the time that it was half-life. I'll just actually write it right here right now. Let's see, half-life from graph. Yes, I misspelled the word. Half-life from graph. There you go. Make this bigger. And I said it was 897 seconds in my case. Okay, and again, make sure you use your units so I know what kind of time you're measuring in. Okay, now we're going to do a calculated half-life. How do we do that? Well, to do a calculated half-life, we need to use the K value that we calculated. So here, you can see that the value of K, 0.007, even though there's a negative number in there, ignore the negative number. There is no such thing as a negative rate constant. All rate constants are positive, okay? So just use 0.007 as your K. And make sure you report it positively too, even if it shows negative, because you will get points off if you have a negative K. So this is going to be calculated half-life, calculated half-life. Oh my God, I keep misspelling. There you go, calculated half-life. And this is going to be from the formula. So using K, I know that half-life is equal for first order reactions, which we know because it gives us a straight line. So that is going to be equal to 0.693 divided by 2 times K, which is 0.0007. I think that is the right formula. And then that is going to give me 495. Okay. Was there a 2 or was it just K? I think it was just K. There you go. That looks a lot better. Yeah. So I got the formula wrong for that. But again, you can look up the formula. You don't have to be listening to me. Okay. I'm just teaching you how to do the graph. So you could see when I get the formula right, it's this number 0.693 divided by K. That gives me the T1 half. And the T1 half is very close to the observed T. So this is actually some very good data right there. And it proves also that our rate constant is pretty spot on. You know, this is one way that we can measure accuracy and precision. So make sure that you calculate half-life. If you need help, you can always Google half-life formula for first order equation. Okay, 897 is very close to 990. Yeah, it's off by about 100, but the numbers are close, much closer than the original calculation I had. Make sure that you are putting your milliliters in liters. Please don't make that mistake. If you used a different concentration of sodium hydroxide on day 1, and I think there was a slightly different concentration on day 2, please make sure that you calculate the corresponding numbers together. Okay? Other than that, the rest of the information should be in your lab workbook. All you have to do is go to where it says day 2, and it tells you how to calculate the data. It tells you what belongs to what, and it tells you how to do it. If you still have any questions after watching this video, please let me know. The labs are going to get more intense. You do need an introduction that is typed out on Microsoft Word. You do need your procedure and experimental also typed out. Just tell me what you did. It should not be one to one exactly the same as the lab notebook. Even if you did exactly the same thing, things don't always go exactly the same. Maybe you overshot it. Maybe you used a beaker instead of an Erlenmeyer. You need to describe what you did. Pretend it's a journal diary entry and then tell me what you did. You can put step one, step two, whatever it is. It shouldn't be too long. Just, give me a short summary of what you did, what happened. If something went wrong, tell me that it went wrong and tell me how you fixed it. And then other than that, it should be good. So if you have any more questions, feel free to watch the video as many times as you need to. I do apologize if there are parts where there's a little bit of confusion due to my attempt to resolve the problems. Watch the video and see how I solve the problem. Learn how to use Excel. Don't be depending on the videos. You can always Google things yourself. You can always look things up. ChatGPT has been known to not give accurate Excel advice, so I would still disavow and discourage you from doing that. But other than that, thank you for your attention. Let me know if you have any questions. I hope you guys have a good weekend, and I'm always available if you need anything. So thank you very much, and have a good weekend and have a good night.